So verification. So if S1 is equal to 1, S2 is equal to 1, because these are arbitrary constants, so just for the sake of verification, we can take S1 and S2 is equal to 1. So U will be then equal to 1 minus 2 is minus 1, minus 1 plus 4 by 3, it is 1 by 3, and 1 plus 0 is 1, and 0 plus 1 is 1. So this will be U. So now this U has to be orthogonal to both of these vectors. Okay, so let me write it down, these two vectors here. So what were those two vectors? So one was this A, which was 1 0 minus 1 1 0 minus 1 2. Okay, this is this vector, so we call it as A, and the other vector was B 2 3 1 0 2 3 1 0. B is B is 2 3 1 0. Okay, so and U we found as minus 1 1 by 3. So if I take like A dot U, so U will be minus 1 1 by 3 1 1. So what will be that? 1 into minus 1, 0 into 1 by 3, minus 1 into 1, 2 into 1. So minus 1, 0, minus 1 is minus 2, minus 2 plus 2 is 0, so it is 0. And so that means A dot U is 0. And how about B dot U? B dot U, so U will be minus 1, 1/3, 1 1. So it will be 2 into minus 1, 3 into 1/3 plus 1 into 1 plus 0 into 1. So it is minus 2, 1, minus 1 plus 1 is 0. So it is 0. So it means that we have verified that AU is both orthogonal to A and B. But in this case, the final answer for us is the basis for this vector U, which is the S perpendicular. So the basis is these two component vectors, okay, with the S1 and S2 as the free parameters. Okay, next example is okay, this is the last one for this section. The next example is we have to verify that S vector. So let me write the S vector first. S subset is the combination of 3 vectors. That is the S subspace. Subspace is 1 2 minus 1, and 1 minus 1 minus 1, and 1 0 1. So if we have a subspace of this 1 2 minus 1 1 minus 1 minus 1 1 0 1, you can actually verify that this is a valid subspace. These 3 vectors are independent with each other, and we have U 2 1 1. Okay, so we have to verify that S is a orthogonal basis for R3, and use this to write U as a linear combination of the given basis vectors. So this is an orthogonal set 1 2 minus 1 1 minus 1 minus 1 1 0 1. This is the same set which we first we have to verify it. Okay, so first part of this question is verify that S is an orthogonal basis. Okay, orthogonal basis for R3. So first we have to verify that this is orthogonal. So this we have already verified in the previous one of the previous examples. 1 2 minus 1 1 minus 1 minus 1 1 0 1 here. In the part A. Yeah, 1 2 minus 1 1 minus 1 minus 1 1 0 1. So here we took these three dot products and all of these dot products were 0. So S is an orthogonal subset. And the next part is by this simple inspection we can also see that all these three vectors are linearly independent, and therefore we can see that this is also the basis in R3. Okay, a basis in R3. So now the next part is that can we represent these vectors? So suppose, let's see, we say these vectors as S1, S2, S3, and if these vectors are orthogonal, so we have we can represent these vectors as a combination of as components of this and any other vector such as U. Okay, as component of any other vector such as U. So in this case U will be equal to C1 S1 plus C2 S2 plus C3 S3. Okay, so we need to find the values of C1 C2 and C3. So that means okay, so that means I repeat, so if S1 S2 and S3 are orthogonal, okay, and then they form the basis of certain subspace, then we can have their combination, certain combination. We can always find a certain combination to make them equal to U. Okay, so for this given vector. So so according to the theorem given in the book chapter, C1 we can find by this S1 dot U over norm of S1 square. So let's do it quickly. So C1 S1 is okay, S1 is this. So S1 dot U will be 1 times 2. It will be 1 times 2 plus 2 times 1 plus 2 times 1 plus minus 1 times 1 minus 1 times 1. And then what will be the norm of S1? That will be this, because the norm of S1 is the square root. Square of the norm is without square root, so there will be no square root. So norm of S1 will be 1 square plus 2 square plus 1 square. So it will be 2 plus 2 4 minus 1 is 3, so 3, and then that is 4 plus 2 is 6, so it is 1 by 2. It will be 1 by 2. C2 will be then S2 dot U over square of the norm of S2. So S2 will be then S2 will be then 1 into 2 minus 1 into 1 and then minus 1 into 1 minus 1 into 1. okay, and then it will be 1 square plus 1 square plus 1 square. So what we get is 2 minus 1 is 1 and 1 minus 1 is 0. So 0 over 3, that is 0. So SC2 will be 0. And then C3 will be S3 dot U over S3 norm square. Okay, sorry, S3. So what will be S3? S3 is this 1 dot U, 1 into 2 plus 0 into 1 plus 1 into 1 and divided by 1 square plus 0 square plus 1 square. So 1 square plus 0 square plus 1 square. So what you get is 2 plus 1 is 3 over 3, that is equal to 1. That is equal to, no, 1 plus 1 is 2. So that is 2. So it will be 3 by 2. 3 by 2. So it means that we can represent this vector u, which is 2 1 1 2 1 1 as equal to 1 by 2 times S1. S1 was 1 2 minus 1 1 2 minus 1 plus 0 times S2. S2 was 1 minus 1 minus 1 1 minus 1 minus 1 and then 3 by 2 S3 1 0 1 1 0 1, and even we can verify it. So it will be 1 by 2 1 minus 1 by 2 the second one is 0, and then this will be 3 by 2 0 3 by 2. So what we get is 3 by 2 plus 1 by 2 is actually 2, 1 plus 0 is 1, and 3 by 2 minus 1 by 2 is 3 by 2 minus 1 by 2 is 1. So it will be 2 1 1. So it is, this means that we have expressed this vector. So in this way, then any sets of vectors which are orthogonal can be represented to be equivalent to some other vector by multiplication with some constant, and these constants can be found by very conveniently by these by these relationships.